So today we're going to look at the z-test for the difference of two means, and this is particularly helpful because it helps us make a direct comparison between two different populations that are being compared, both with an average value. Think back to what we talked about with confidence intervals in doing a difference of two means confidence interval. Okay, in that case, we were looking to see if that interval crossed zero because we weren't looking at the populations individually. Instead, you're looking to see if there was a significant difference between those two groups. And if that interval included zero, then you're saying that there could be zero difference between these two. Okay? But if there was a significant difference that was entirely positive or entirely negative, then you're saying that you have confidence that there is a difference and it's between these two values. Okay? The z-test answers that question about is any difference that we see between these two averages, is that significant or not? Okay, so we see our target there, test the difference between two sample means using the z-test. Now, there are some assumptions that go into this. Okay, we're only allowed to use these equations if it satisfies these conditions. Now, sometimes, myself included, we're guilty of kind of assuming that these are met, but we really should think about if we're allowed to use these sets of equations. Okay, both samples need to be random samples. The samples should be independent of each other, which means that if you're comparing these two populations, it's not just that you have one group answering one way and then everybody else is automatically in the other group that's being compared. Okay, obviously those would be dependent of one another. Our third assumption is that we must know or be able to find the standard deviations of both populations. Okay, if the sample sizes are less than 30, those populations need to be normal or approximately normally distributed. If they are less than 30, we should really use a different test, which is a t-test, which we might take a look at a little bit in the future here. We see some equations at the bottom. This is talking about what we're doing with this difference of two means test. You can see on the far left here, this is the very general equation for what that difference of two means test looks like, where you have one mean, subtract away the other to get that difference, and then you're dividing by a standard deviation calculation for this test, which is called the measure variability. And remember the measure variability, we got that from when we were doing our confidence interval for this. You're finding individual standard errors of the mean for the two populations. And then once you have that, you're squaring each of them, adding them together, take the square root, and then all of that contributes to this entire equation here for the difference of two means. Or honestly, the easier thing is to use the calculator. So that's what we're going to take a look at with our example problems today. So let's take a look at our first problem. This is from our book notes. We talked about this when we were looking at confidence intervals. It's two groups of people that are looking to lose weight. One group is doing it through diet alone. The other is doing it through exercise alone. So we see some important values here. We see the sample mean for each group. We see the sample standard deviation for each group. And we see the sample size for each group. Okay, those are the 6 things that contribute to the equations that we saw on the previous page. You see the 2 x bars are the 2 means, the 2 s's are the 2 sample standard deviations, and then the 2 n's are the 2 sample sizes. But what we are going to do is let the calculator take over for us here. So our hypotheses, the null hypothesis, again, always some form of equality. When we were looking at a single sample, we were always comparing it to some null value. But when we're comparing two populations to each other, okay, we are going to say that there's no difference between these two populations, or the mean for the diet group is equal to the mean for the exercise group. Okay. Now, you could have greater than or equal to or less than or equal to, but a lot of times you see this as just an equal sign where the two are the same, and then therefore the alternative hypothesis, really going into this, we have no idea if one's going to be a more effective method at losing weight than the other. So we're just testing to see if they are different. If the average weight loss for the diet group is not equal to the average weight loss for the exercise group. Now, if you had an indication that one was definitely going to be greater than the other, or it wouldn't make sense for one to be smaller than another, then you could make this a one-sided. But more frequently with the difference tests for means and for proportions that we'll see later this week, you see a two-sided alternative hypothesis, okay, meaning that that not equal sign is there. So as I said, we're going to let the calculator take over for us here. So let's take a look at the graphing calculator, and we're going to go to Stat, over to Tests, and for a difference of two means, we are looking at a two-sample z-test, which is number 3 on the calculator. So enter that. And once again, you have two different tabs here for giving it all the relevant statistics that you need, or if you're wanting it to pull from the lists, that's under the Data tab. We're going to look at that in our next problem. But for right here, let's go with the stats. And the first thing that's entered is the standard deviation. Now remember that ideally this is population standard deviation. Oftentimes that's not practical to have that, so we're just going to use the sample standard deviation for each of these. Notice the subscripts there. Make sure you're keeping them together. Like, let's let group 1 be the diet group and group 2 be the exercise group. So we're asked for those two standard deviations first. That will mean that the diet group standard deviation was 4.1. Exercise group, their standard deviation was 3.7. Now we want the mean for the diet group, which was 5.9 kilograms. And the sample size for that diet group was 42 people. The mean for the exercise group was 4.1. And its sample size was 47 people. Again, the two samples don't need to be identical in terms of size. However, they should be independent from one another, like we looked at in those assumptions. Last thing, we have these are giving us a two-sided alternative hypothesis, so we want to make that mu1 is not equal to mu2. And now we can go down to calculate, and we get our z-score and our p-value that we see right there. So we'll take this back to our other screen. Our z-score was 2.16, so we're 2.16 standard deviations away from the center of this normally distributed set of differences. And our p-value was 0.03, which is less than 0.05. So we reject the null and accept the alternative hypothesis, meaning in this case that we do have significant evidence that there is a difference between the average weight loss with these two techniques. Okay, that this difference of 5.9 kilograms over 4.1, that is a significant difference. So we have evidence that there is a more efficient method of weight loss if you're just picking one of them, and that appears to be diet alone over exercise alone. Our next example is pulling from some raw data sets. It says a researcher hypothesizes that the average number of sports that colleges offer for males is greater than that for females. A random sample of the number of sports offered by colleges for males and females is shown. The alpha level 0.05. Is there enough evidence to support this claim? Assume both population standard deviations are 3.3 sports. So we have no averages provided for us. Instead, we have 50 male sports at colleges and 50 different females sports or colleges that offer female sports. And the numbers that they provide are given there. Now, again, we're making an assumption that these are independent of each other, that they're randomly selected, and they're representative of a larger population, probably nationwide schools. So let's create our null and alternative hypotheses. Null hypothesis is that the two are the same. Okay, this is the safe hypothesis, so that the average for males is equal to the average number of sports offered for females. In the alternative hypothesis here, now look at the wording of the problem. Okay, the researcher hypothesizes that the number of sports that colleges offer for males is greater than that for females. So this wording indicates that our null hypothesis is going to be that the male value is greater than the female value. So this is a one-sided alternative hypothesis. So going to the graphing calculator, for this one, we need to enter the data into the lists, and to save some time, I've already done that. L1 and L2. L1 I have the male values, L2 I have the female values. Make sure that you are very careful when you're doing this, especially if you're using this emulator. It's very difficult to enter some numbers, especially like the number 11 where you're repeating the digit. If your raw data is wrong, you're going to get different answers. So just be aware of that. I took my time and was very careful in entering these numbers into the lists. So we'll go over to stat and tests. And again, this is a difference of two means. So number 3, a two-sample z-test. And for this, we're going to go to the data tab and have it pull from the lists. Now it still wants us to have the opportunity to enter a population standard deviation if we have that. So it's said in the problem that we're going to let both of these be 3.3. If you did not have this, then you're going to go to either one var stats and do it twice, or two var stats and get the sample standard deviation from each of these lists. Okay? But the rest of the data, like the means and the sample sizes, it's going to pull from L1 and L2, so it's important to verify that those numbers are correct. And then our last one, the alternative hypothesis. In this case, we have the male values in list 1. We are hypothesizing that those are greater than the female average. So we want to go over and make this a one-sided alternative hypothesis where mu1 is greater than mu2. And then down to calculate. And we have our values here. Our z-score is 0.94, and our p-value is about 0.17. So we'll go back to our page here. Z-score 0.94, and our p-value, p is equal to 0.17, which is not less than 0.05. So in this case, we fail to reject the null. Meaning that, in this case, we do not have enough evidence to say that there is a significant difference in the number of sports offered at these colleges between males and females. Okay, maybe that evidence is out there. Okay, we don't know that. Okay, so in this case, we believe that the null hypothesis is true. It's worth mentioning, I didn't do it in our previous problem, that if we made an error, okay, this would be a type 2 error. Okay, because we believe that the null hypothesis is true, the original. Okay, if that is not correct, then the second hypothesis is true. Okay, the number of the error is the hypothesis that is actually true. We did the wrong thing. Okay, so this has the possibility of a type 2 error. On our previous problem, where we rejected the null and accepted the alternative hypothesis, okay, we believe that the second hypothesis is true. This opens the door for a possibility of a type 1 error. And again, the probability of that type 1 error is the p-value. So there's a 3% chance of that happening, that we did the wrong thing. We're willing to take that risk in this case. We said anything under 5%, that is rare enough that we will accept the risk of that error. Okay? So what I'd like you to try right now is this third problem. You do not have to worry about raw data on here, but read through this example and perform a difference of two means z-test.